So I call this a very quick dip into materials combinatorics because almost everything that we do is a combinatorial challenge. And what we do in the materials project is take these combinatorial challenges and we say, how do we develop a data-driven methodology for tackling them? So the example that Kristin gave of discovering a novel battery material is fundamentally a combinatorial challenge. And so, in the end, what we do is we take these challenges, we say, what can we compute? How do we compute it? How do we automate that computation? And then how do we mine the data set so we can get some better understanding of what's going on? So one of the challenges that we've been working on for some time now is really the problem of piezoelectric materials. Piezoelectric materials are a type of material that when you either apply a stress on them, you get a polar response, a charge response, so you get a voltage, or if you apply a voltage to them, you get a mechanical response, so you get a strain. These are kind of everywhere, from actuators to the, actually, they're probably, if you use an AFM or anything that has a nanometer level precision stage, that's probably a piezoelectric driver that's actually moving that stage. It's used for large scale industrial processes. It's kind of everywhere. It's probably in your iPhone. The RF filters are piezoelectrics that are also there. So it's a very ubiquitous material. But almost all the known or all the most useful versions of piezoelectrics are lead-based. And it turns out this family of lead-based piezoelectrics is pretty much the only commercially viable version. And so we really need to move away from that. And so in MP, we try to figure out if we can design novel piezoelectric materials, specifically ones that are not lead-based. And when you look at this space, one of the things you always come back to is this idea of a morphotropic phase boundary. So on the left, I show like a very simple phase diagram for the PZT system, so lead, zirconate, titanate. And really one of the things that in engineering that you're taking advantage of is that a certain composition, there's a very kind of vertical phase boundary between two different phases of PZT. And near that phase boundary, you get a very strong piezoelectric response. Now, not many materials, in fact, there's no good engineering material that has the same kind of morphotropic phase boundary. And this is an alloying system. So from a computational standpoint, it's a very complex combinatorial problem. We have to specify the position of every single atom in order to compute something. And if I'm talking about a 50-50 alloy, I could be talking about hundreds or millions of positions in order to compute anything. And if you've ever played with density functional theory, which is the tool we like to use in the materials project, you're not really going to scale beyond, say, 100 to 200 atoms. So it's a challenge in the sense that there's very difficult to compute something on that large scale. The combinatorics are a challenge, but we don't really have good tools to scale there. What we did is we basically asked, what are the fundamental properties that actually dictate piezoelectric response? And it turns out one of the most important properties are the phonons. This is effectively the way in which atoms vibrate together in order to support thermal transport or just the thermal fluctuation of the system alone. So the phonons are really critical to describing how this piezoelectric response occurs. And if we could just describe the phonons, not the material itself, not the atom positions, but just the phonons in that alloy composition, maybe we can have a better idea of how to compute piezoelectric materials and even alloys that would have strong morphotropic phase boundaries. So we get around this combinatorial challenge of specifying every single atom. There's a paper we recently published where we did this for PZT and other different systems. And what I show you on the right is basically the relative change in the piezoelectric response as you kind of perturb these phonons in the system. And if you look at the systems in which people have designed that are non-lead based, where you can alloy them a little bit, but they tend to really lose their piezoelectric response, you find that there's only one phonon response that's actually, or only one phonon mode supporting all the piezoelectric response. So you can think of it just like there's a single oscillation that's providing you a piezoelectric response. If you scramble in any way, it's all gone. If you look at the lead zirconate titanate system, it turns out there's actually multiple phonon modes that are responsible for this. And so as you increase or perturb these phonon modes, even though you might scramble one of the phonon modes, you have other phonon modes that are still supporting your piezoelectric response. And that's part of the reason why it makes such a good alloy system to play with. We used this kind of behavior, this fingerprint, for the perfect systems to then go and look for novel systems that we can try to make and possibly predict strong piezoelectric response in an alloy system. And there's a number of different choices that we looked at, like tantalum phosphates, a couple different oxides like strontium niobate, and these are all systems that people have not really explored, but maybe have made for other purposes. And in doing that, these are actually materials that we're right now in the materials project on a very small experimental collaboration team trying to actually synthesize and test for this kind of behavior. Oh, there we go. So on the other side of this, Kristin mentioned that we have primarily an inorganic database. We do have some organic molecules. There's about 20 to 30,000 molecules that are associated with electrolytes. So this is really for battery exploration. And one of the critical challenges in battery systems is really trying to understand the evolution of what's called the SEI. This is effectively a layer of gunk that builds up due to decomposition of these organic electrolytes at the anode and the cathode. And you can think of these anode and cathode regions as extreme environments because the potentials are so strong. So what we'd like to do is figure out how do we understand how the system evolves. At the bottom here, I have kind of a depiction of a very simple, what we call a reaction cascade. Even though the electrolyte's only composed of a couple different elements, it actually goes through a lot of different intermediate states in which bonds are broken before it forms what we think are the components of this SEI. So lithium carbonate, lithium fluoride, LEDC, lithium hydroxide. These are all things that could form the SEI, but we don't know how the SEI or how the system gets there. So what we started to do is we actually took the molecules that are in the SEI or in the electrolyte, and we started to break them in DFT one by one. So we just took a bond, broke it, took a bond, broke it, and kept on doing that until we built a large database, about 30,000 calculations of every way in which you can break these molecules. The result is that we can start to actually follow how these bonds can break in certain sequences, how they can form back in order to create the different elements of the SEI. To give you an example, if we have 30,000 calculations or different molecules, there's something like 100,000 different reactions we can model. And this is a combinatorial problem because as you continue to grow and grow the base set of information that you have, the number of reactions kind of grow unbound. So this is another space in which we're now starting to look at things like graph algorithms. So how can you use graph walks or even graph neural networks to try to identify, are there bonds that are most likely to break if I just give that neural network algorithm any single molecule, or can there be a certain sequence of breakages of bonds that are actually more favorable than what we traditionally think? So we actually built an algorithm to look for these kind of more favorable reaction pathways. And so an example here is basically a reaction in which lithium plus ethylene carbonate effectively decomposes into LEDC. In blue is really a reaction path which has been kind of theorized in literature for a number of decades now. And one of the fundamental flaws with this reaction pathway is that it kind of uses our human intuition. Every time I get a chance, I should take the most exothermic possible step. And that puts you into a valley in which you have to take a rather expensive step in terms of energy in order to get to an intermediate state where you can end up at LEDC. Because we're not biasing ourselves to these kind of these exothermic steps, we actually were able to find with this reaction network a pathway that maybe has a much smaller step in terms of going uphill in energy, but as a result, it's actually very easy for this intermediate to then transform into the LEDC. So we think this is actually a much more likely step of how an SEI is forming than what people have at least postulated in the past. So I just posed up two different concepts of combinatorial challenges that we're tackling. I think these are good kind of ways to think about it, in which there are combinatorial challenges that are implicitly combinatorial, such as kind of the disorder, right? It's something that's very difficult to model because there is something combinatorial about it. But if you transform yourself to a space in which you're kind of eliminating the combinatorial aspect of it, you can probe other critical properties. The other is the explicit combinatorial challenge, such as the reaction networks. That's just going to keep growing. And so we have to employ computational algorithms to really tackle this space. And that's a big area of development for us. And then I just want to make sure I have any chances for questions in case at this point in time. Oh, chat.
There is a question from Wan Liang.
Yep.
The MP found or pinned down new organic species in the SEI component in addition to the reaction pathway findings?
Yeah, so this is a really good question. So when you look at literature and people try to plot the pathway between what is put into the electrolyte and what we think the SCI is made of, often we ignore what we call our byproducts. There are things that actually have to form along the way, and we postulate these reaction pathways, so we think those are not important. In the reaction pathway that we find, we do think there are other byproducts, but the issues really are is that those byproducts should not be that long-lived. So the question becomes, what do they form? And when you start to really look at all these other pathways, you see lots of possible reactions that can form. There are two critical challenges that we still have to tackle in our reaction network. We are information limited. We can only compute what we know, and what we know are what people have either put into the electrolyte or what people find, or they think they find at the end of the electrolyte once it becomes an SCI. There are other things that could form in between, and we use some fragmentation to try to find those, but we really don't have good algorithms to put together random fragments and make larger superstructures that may form. And so we don't know some of the things that are going to show up simply because they can kind of attach back together and then decompose. And we're working on algorithms to try to find those as well. Oh, sorry. Any other questions? Okay, so I will move on to the next step. So before I go into the tutorial, I want to just highlight this. We've built a community forum we call matsci.org. It's segmented throughout or based on some of the projects that we have. So there is a section for the materials project. There's a code that we have called Atomate, which is really our high throughput workflow. So this is how we run DFT calculations kind of automatically. And there's a section for something called MapMiner, which I'm going to walk you through in a minute. And this is a really good place to go and ask questions, partially because the materials project team tends to spend a lot of time on here answering questions, but also we're hoping that more and more people are actually answering questions. And we find that as we grow in community size, that does tend to kick in. The other thing I wanted to highlight is that we do have an upcoming virtual MT workshop. Typically, this has been in person, but because of the current health crisis, we've decided to make it virtual for this year to see how that works out. It's going to be July 28th to 30th. It's 2.5 days, and we go from 0 to fully using MP tools. So the idea is, even if you don't know how to use Python, you can come on the first day, and we'll basically walk you through a primer to teach you how to use Python. We'll teach you how to use MongoDB, which is a database that we use. And then in day 1 and day 2, we'll basically go through some of the critical tools, such as PyMatGen, which is a kind of our material science library, and Atomate, which is how we perform all our high throughput calculations. And finally end up with MapMiner, which is what we're building for machine learning and material science. It's very hands-on. The idea is that we'll walk you through tutorials, and I'm going to walk you through a tutorial just in a bit. It's going to be in a similar flavor, but you'll have helpers constantly there to answer questions, to help with any issues, if there's any errors, or if there are things that specific questions that you have. It's a very useful way to really get access to the materials project team. I've also got the link at the bottom, and I think I'll have Antoine send out that link after this as well. So that's the end of the slideshow. What I'm going to do next is actually switch my screen. To my Chrome. So I think everyone can see my the website MapMiner. So as I mentioned, this is our package that we are building for the explicit purpose of really doing machine learning in material science. MapMiner is spearheaded by Anubhav Jain, who is also a research scientist here at LBL. He is actually one of the co-founders of the materials project with Kristin and Gerard Sater when they started in 2010. He was the postdoc that was charged with making this all work in the beginning, and we get to basically take what he was able to succeed at and grow it continuously. The idea with MapMiner is that it hooks into all of the existing Python machine learning tools that you've probably heard of, scikit-learn, PyTorch, etc., and it makes it very easy to start doing some machine learning. There's a pretty big documentation, and so there's a lot of information about how you retrieve data, you access these data sets, you can build descriptors, and I'm actually going to click on this button down here, which says examples. And so if anybody else wants to follow along, you're more than welcome to. You don't actually need your own local Python environment to be able to run these examples and actually play around with this environment. So I click examples. You'll see there's a couple different things here, and this example number 1, which says use MapMiner and scikit-learn to create models that predict the bulk modulus of materials. There's a link that says Jupyter Notebook. If I click on that, nope. Let's see again. take a second for it to load. There we go. So this is an example Jupyter notebook, and one of the nice things about this is I can actually click on this little button up here, which says execute in binder, and you'll get a custom Python environment just to run this notebook. So I'm going to click on that. It'll take just a little bit to load. In the meantime, we can kind of just look at this notebook. Oh, there we go. It's starting to load my binder, so now it'll start building that repository so I can play around with it. In the meantime, we'll just start looking at the notebook and to see what it's doing. So, you know, MapMiner has everything that you need in terms of being able to get data, build machine learning models, and then actually investigate what those models are doing. So at the beginning, what we basically do is we'll load the data set using a convenience loader. So there's this nice load elastic tensor data set, and this actually changes as the elastic tensor data on materials project updates. So as we add new tensors, the load elastic tensor set will actually bring those in. There we go. Give it a second. So in a Jupyter notebook, if you haven't seen this before, there's a couple different ways in which you can interact. There are these cells which are called markdown cells. So this is listed as markdown right up here. And this is basically just text information that I can put. It's somewhat formatted. It gives me a way of describing what I'm doing. In this example, it's basically saying, what is this notebook for? It's an example for trying to predict the bulk modulus, overview of what the steps are, and how do you process the data. Now, these cells in here, where the highlight is in green instead of blue, switch this markdown or this pull down into code mode. And what that means is that this is an executable piece of Python code. So I'm actually going to increase the text size just a little bit so that people can see this a little bit easier. So in this first cell here, basically what I'm doing is I'm importing this convenience loader to get my elastic tensor data, and I'm just running it into a variable called df. And there's a little piece of code that's there that says that this is basically going to load it into a pandas data frame. So if I hold down shift and press enter, it will start to run. And in the background, it fetches all the elastic tensor data from 2015, which is already pre-zipped up within MapMiner. And it says it's no longer showing a star here, which means this is done. Now, pandas data frames are pretty standard in the machine learning or data science world. They are basically a tabular format that lets you hold whatever you want in there. In our case, we actually have materials project structures also within the data frame. You can have numerical value, you can have images, you can have machine learning models for all you want. It doesn't really matter what kind of fundamental data is there, it's merely an organizational structure. Every data frame has a couple different properties. In this case, there's a function called head. And all that means is that it's going to look at the first, I don't know, maybe 10, 20 different elements so you can get an idea of what the structure of the data frame is. So if I run that, I can see that basically it's output the data frame, and the data frame is completely scrollable. So I can see there's lots of information here. There is a column called material ID, and these are the unique identifiers we use within the materials project. So MP, materials project, and then a dash and a number. We had a colleague who at one point in time, if you gave him an ICSD ID, he could kind of tell you if it was experimental or not, simply by the number. He kind of had an idea that the lower number ranges were experimental and the much larger number ranges were probably not experimental. The same kind of notion can come with MP, except the original structures in the materials project were all focusing on elementary and binaries. So in the low number ranges, MP33, MP100 something, even a few thousand, those are most likely binaries, a few ternaries that are very important materials for batteries, and the elements. As you scroll up in higher and higher number, I think at this point we're over 1 million in terms of MP IDs, so MP 1 million something something. Now you'll see a lot of materials that are theoretical that are coming out of various studies, and we're really designing those for either machine learning problems or discovery problems. So in the data frame, there's a couple different columns that are available within this data set. There's the material ID, there's a nice reduced formula, there's this n sites, which just tells you how many sites do you need in order to describe the structure, the space group, the volume. There is this structure column, and as I mentioned, we actually store the structure object itself within the data frame. And then there's a couple other properties that are related to the mechanical response. So there's the anisotropy, the shear modulus, the bulk modulus in the 3 different forms, the Voigt-Roos-Hill and the Voigt-Roos-Hill average, the Poisson ratio, a compliant and elastic tensor. So these are full 6x6 tensors, and the original value that was not symmetrized. So there's a lot of information here by a very simple one-click command. And you can actually go through this if you want to and get a better understanding of what's going on. We're so far only looking at the data. Let's look at what is actually in here. So if I do this, run this df.columns, basically this tells me what's available in terms of the data frame. So there's the material ID, there's the elastic tensor, all the other things that are there. For the purpose of this exercise, I really don't need most of this information. If I want to predict the bulk modulus, I really need a few things. I need the structure, so I need enough information to describe the material, and I need the bulk modulus. So I'm actually going to get rid of everything that I do not need. So in this case, I have volume and size, compliance, elastic tensor, most of these other things that are unwanted. So I'm going to get rid of them. And if I check what's left, I have a few things. I still have the formula, the space group. I'm going to keep that anisotropy for now, the shear and bulk modulus, and the Poisson ratio. So this is the simplest description of the various elastic constants or the elastic properties of these materials. Scroll down a little more. Another very useful feature in pandas is describe. So what this basically does is give you a summary of the information. So for now, because if we go up and look at what's in our data frame, we have the material ID, the formula, we have space group, structure, anisotropy, bulk and shear modulus. We have basically a couple different things that are numeric in nature, so space group, isotropy, anisotropy, the bulk and shear modulus. If I run this describe, it will actually try to describe those columns. And for those numeric types of properties, elastic anisotropy, bulk, shear modulus, Poisson ratio, these are kind of useful, right? Mean, standard deviation, min, 25, the quartiles, and the maximum, these are useful. But you'll also notice that it did this for the space group. And so this is a peculiarity of machine learning in general, I would say, which is that representation matters. For our purposes, we're using a numeric space group, but we have an idea of what that means. It's categorical in nature, right? If I take space group 182, I can't just subtract 100 and get to space group 82 in a meaningful way. There's no way to describe that operation unless it has some kind of hierarchical relationship. All I'm using the number is for a way to index the space groups in an efficient manner. So in this sense, even though describe is giving me information, it's kind of not useful just because I have no way to interpret what's going on. If it told me kind of the distribution of space group as a function of those numbers, that might be more useful. So let's go down a little more and start doing some featureization. So this is where MapMiner gets really interesting, because this is where we start to kind of link in the material science understanding. And the basic idea here is that in order to do machine learning in material science, in chemistry, even in astrophysics, even in biology, you often need some intermediate space that describes the properties. We as scientists have an idea of how the bulk modulus can be described. We as scientists have different ways of thinking about chemistry that's based on the composition, or how the space group and symmetry relations actually kind of control the properties of the material. And we need a way to go in and say, if I give the machine a structure, it can then automatically generate all these other things. So MapMiner has a series of features called, or series of tools called featureizers. And I'm actually gonna break this up first. So I'm gonna say, basically in Python, I'm gonna import this string to composition featureizer. What this does is it converts this formula into a composition object. But before that, I'm actually gonna delete that string to composition, let this be open, hold down Shift and press Tab. If I press Tab twice, it might take a second for this thing. Let me go ahead and import this first so it knows what it's talking about. And then make another cell below it, and then say from mapminer.featureizers.conversions, import. And now the tab, it gives me autocomplete. So I can actually start to look through all the things that are available. This is basically what's available in Jupyter Notebook. Oh, need to type that correctly. There we go. So this is the list of the various featurizers that are available. This is also in the documentation, but I'm kind of just showing you how you can start to explore it. So you can see that there's composition, which is something that I would actually use within this, which is actually an object that I want. But there's composition to oxidations, or oxidation state decorated composition. There's structure for materials project. There's string to composition, there's structure to composition, there's structure to oxidation structure. These are all various featurizers that you can basically apply on a data frame and automatically get all these features added. So I'm going to basically first do the string to composition, and after that, I'm going to paste back in the code that I had before. So all this is saying here is I initialize that featurizer, and then I basically take the data frame, and I wanted to apply whatever string to composition does on formula. So I shift enter, it goes through, gives me a little bar of what it's done. And then if I look down here, I can see that formula is still there. And that, but instead I have this composition field, which actually has a composition object. And this is just a summary of what's in that composition. Now, the real power of something like this is when you have, say, a composition object, now you can go through all the featurizers that are available in MapMiner that are based on the composition of the elements. So a very simple one is something called the MAGPIE dataset, which is a way of convoluting the oxidation state, the kind of general electrochemistry, the electronegativity, the metallic and covalent radiuses, and kind of put them all together to create these kind of features that represent the chemistry on an element by element basis. In order to do that, we go into MapMiner, we go into the featurizer set. We basically then go into this module called composition. So these are composition related featurizers, and we import element property. What I'm going to do very briefly is show you how to start exploring those featurizers a little bit more. So we'll start by going into mapminer.featurizers. And if I just press the dot and press tab here, it starts to list all the modules that are available. So you can see that if I have a band structure, I can actually featurize that band structure. And that might be the curvature of a band, that might be the effective mass for that band structure, and that might be the various branches that are available, the Fermi level, the band gap, various featurizers that are available to you to go from a band structure and start machine learning directly on band structures. And I mentioned this because Materials Project does have tens of thousands of band structures that are available, and there's lots of electronic structure properties, such as the effective mass, that are very important for things like PV applications. There's also composition-based featurizers. There's featurizers for the density of states, so it's DOS, for individual sites and for structures. There's a bunch of utility featurizers that are also available, and then there's this function featurizer, which lets you kind of apply whatever random function you want on any individual data set. So let's delete that. In this specific application, I'm taking the composition module and I'm importing this element property featurizer. I'm going to just very quickly delete that right there so we can take a look at what's happening here. So this element property featurizer has a very nice convenience function called from preset, with the preset name here is called MAGPIE. There's actually a number of other different featurizers that are available. Some basically are SOAP based, which is a way of enumerating kind of the radial basic functions and applying the atomic features on those. Others are geometry based, so they're trying to do some oxidation state, but you can use these to start decorating the data frame. If I take this EP feat and I just look at what it's like, I can press enter and it tells me what it is. So it says it's an element property featurizer. The data source that it's using is the MAGPIE data set, which is just that list of properties that are element based. And what it says is it's going to combine basically the number, the Mendeleev number, the weight, melting temperature for individual elements, the valence number, the number of filled and unfilled electrons, the band gap for the ground state, the magnetic moment, the space group number. It takes all of these features and on a composition level, convolutes them together in order to get various properties, gets a statistical average, so it gets the min, max, range, and these are the features that are used by this featurizer to then do machine learning. So I'm going to print back that or copy or paste that back. So now what I'm going to do is featurize my data frame. So my data frame that I had before, I'm going to tell it to use the composition column and then print out what's going on in just a few columns. So I press enter, it sits there and it churns through these different properties. It tells me how much it's done. It's going through all 1,100 of these. And when it's done, ta-da, you now have a new data frame. Now, if we scroll to the right in this data frame, we have the composition. And now you'll start to see that there's actually a number of different columns here. These are all the various featureizers that it is actually computed. So for each one of these, it's produced an average, a mean, a standard deviation, a range, a min, max, and these will go into our machine learning model. Let's do this instead. Let's press B on that cell to give us one more cell to play with. And what I'm going to do here is I'm going to say df.columns. And you can see that there's actually way too many columns here. There's 141 of them in order to actually, that are actually available. If I instead convert this to a list, I believe this is the function, it's .toList, I can now see what's all available. So the initial features that I had in the data set and all the various magnified features. Now, some of you might ask, well, why do we need featureizers? Why not just let the machine learning model do all the work? If I just put this into a neural network, eventually it will get me something, and somewhere in between, these will show up correct. And the problem is that's not true, right? So machine learning models in general, there's two aspects of them. One is garbage in, garbage out. So you need a good data set. First of all, you need to really understand your data set and what it encompasses in terms of how it limits your inference, how it limits your, what you can actually predict. But the other aspect of it is that if it doesn't have some way of producing the features that it needs, then it can't actually rely on those, right? And so concepts like electronegativity, concepts like the valence structure, concepts like the elemental melting temperature are not something that any machine learning model or neural network is going to be able to pull out of thin air. It has to be given this information. More importantly, it has to be able to understand how to take that information and convolute it on whatever geometry, composition, et cetera, that you have. This is something the machine has to be fed. But MapMiner basically makes that easy by giving you all the tools in a way in which you can plug into scikit-learn and have all those features available for you. So if I scroll down some more, there's one more aspect of this which is kind of useful, at least for me. There's so many machine learning tools out there today. It's almost too much to follow along. And often, even if you know what to cite, or what you're using, you don't exactly know what to cite. So one of the nice features in MapMiner is, for each of these featureizers, we actually have a citation that corresponds to whatever citation is necessary for it. In this case, it's really the MagPy framework here is what's being cited. So ep.citations tells me that that's the article I need to cite, and it gives me the bib text that I need to use. So I can just put that into my LaTeX document and go ahead and cite that I use this featureizer. And there's other featureizers involved as well. I can go ahead and just get all the citations. So I'll start to speed this up just a little bit. The next thing is to start doing some more featureization. So in this case, we're using a composition to an oxidation composition, and then we're doing something based on the oxidation states. So we first featureize to basically take the composition, so silicon, carbon, nitrogen, et cetera, and we want to decorate it with an oxidation state. We build a featureizer for that. We featureize those oxidation states, and then we look at this new data frame. This is going to churn through it. If I press Shift Enter, so it's using both the composition to oxidation state composition and the oxidation states themselves. So using both those featureizers together, and you can chain multiple featureizers. I'm kind of doing this step by step. Typically, we just figure out which featureizers we want, we run all of them, and then we do the learning or the training after that. If I look at this, I can actually see there's 146 columns, and if I scroll all the way to the right, there's an oxidation state on standard deviation for that as well. The final set of featureizers that this is going to use are structure-based. So there is this density feature, so you can think of this as a way of doing basically understanding the density of what's going on. So this is just looking at the packing fraction effectively. I'll just very quickly run that. And that will take a little bit longer, but the next line is really just saying what are the feature labels that are available. So this is a way to kind of backtrack when you have so many features, where do they come from? So in this case, it's telling me if I run this df feature labels, which I can run with a Shift Enter, says the density, the volume per atom, and the packing fraction came from this featurizer. And so we're finally going to get to the last bit, which is really defining the input and output data so we can do our training. So what I'm basically going to do in this first bit is basically get my bulk modulus, which is my KVRH, so Voigt-Roos Hill. I'm going to say that I don't really need my bulk or shear modulus or any of my other mechanical properties to predict this. So this excluded just kind of controls down what is included in the training set. I'm going to drop those from my training data set, and I'm going to look at all the possible descriptors. If I click on the cell, I'll press B to add another cell, and I'm actually going to take my data cell there, and I'm going to do the head command to take a look at what's available. So I'm including space group, I'm doing all the MagPi features, and I'm doing those few structure features as well. And then let's just do very simple machine learning. So from scikit-learn, I import linear regression, I import the mean squared error, I am basically building that linear regression training model, and I'm fitting for the data that I have. So also to note, this is all being done in the cloud via this free binder platform. So you can modify these notebooks in place if you want to introduce new features, want to play around with it. You can download the notebook at the end, and you don't need to install Python, PyMatch, or any of the tools on your local computer. So that ran pretty quickly. I'll then go ahead and do something called cross-validation. This is, again, within scikit-learn, so publicly available, easy to access. If you want to do any machine learning, this is definitely a package you should learn to use. It's very simple. Cross-validation based on 10 different splits. You take those cross-validation scores, get the RMSE for all those, and report basically the cross-validation. We run Shift-Enter on that cell, basically goes through, you'll let it process, and then it'll finally split out basically what the total cross-validation error is. While that's running, I really want to highlight the last feature of this that's actually really useful, which is plotting. So if anyone else has used plotting in Python before, you've probably used matplotlib, and matplotlib is great. You can customize the heck out of it, and you can get exactly the figure you want. But when you're trying to explore data, it can be somewhat of a burden because you have to tweak it so much to see exactly what you need. The nice thing that we're using now is a package called Plotly, which gives you interactive graphs. And we actually made it really easy to use some of those interactive graphs via this big recipes module within MapMiner. So what I do is I basically make one of these Plotly fig objects. I give it my title, all my axes titles, what mode I'm in, the file name is just where we want to put it, and I can actually have it do an XY graph. So this cross-validation is done, but I'm going to run this very quickly, and it will present an interactive model. So once that plots, and as I mentioned, this is just the tip of the iceberg, right? So once you have these basic tools, you can try other things. You can try random forest. You can start to build neural networks if you want to. You can do all kinds of different data augmentation. All of these tools are available through this binder platform. So I really, really encourage anyone who wants to try to get into these kind of computational methods, either on their own data sets or on the materials project data sets via MapMiner, to go ahead and try this, play around with it, see what you can print, or see what you can do, change the featurizers, change the hyperparameters, change the cross-validation, leave out half the data, see, look at just the perovskites, for instance, and see what you can kind of predict and get an understanding of how the tools work. That's really the most important thing in any type of machine learning application. So as you can see, I have this nice graph, which is basically the DFT predicted bulk modulus versus the bulk modulus predicted from my machine learning model. I can highlight over this, and I can actually see each individual data point. I can zoom in if I want to, and so I can zoom in on some of these outliers, which seem egregious. 121 versus 214. Carbon polymorph, not surprising. Carbon has some very interesting bonding with very weird mechanical properties. So this very simple model probably did not predict it well. So then I can go up here, and I can click on autoscale and get back my full graph. And so this is kind of the process that we use in general, whether we're doing machine learning or we're actually doing more in-depth analysis of any of the data that's available on Materials Project. And as I mentioned, this is only one of the packages that are available. The workshop is 2.5 days, and even that is probably a little bit short. There are so many tools that we have available within the Materials Project. if you have either a material science or chemistry challenge that you think might be amenable to computational methods, feel free to reach out to us and start to ask questions or start a conversation about something that could be interesting science. And with that, I think I've kind of droned on for a while, and I want to see if there's any questions, as well as either this work, trying to do this machine learning yourself and getting data sets, or materials project in general, or the kind of the applications that I was talking about in my slides. Let's see if I can find chat.
So yeah, if you have any question, you can also unmute yourself. If there are too many people, then there's gonna be an issue, but it should be okay. So feel free to speak. Any questions? Not as of now. Okay. Oh, someone is.
Everyone's zoomed out.
And it's pretty cool to see how quickly you can set this up.
Yeah, and as I said, this is all in the cloud, right? So I can do this on my iPad.
Oh, okay.
I can do this on my phone.
Okay.
I wouldn't want to, but I can. And that is one of the things that we're doing in the materials project is, we understand that, a majority of the material science community probably has some Python experience, maybe a little bit, but they don't have experience with our specific tools. So a big challenge for us is how do you make it so that everyone can do the level of computational material science that we're able to practically do or run within a Jupyter notebook. This is a really simple example. I can show you another, if there's no questions, I will show a very simple materials project application. It's going to ask me to log in.
I have a question regarding machine learning. So are there like specific properties that people are trying to predict using these models? I mean, do you get any feedback on what people are interested in looking at, or is it all anonymous, or?
So we are happy if you want to directly talk with us about properties that you think are interesting. I'm more than happy to talk with somebody about that. I'm sure there's plenty of people within the MP team that are more than happy to talk with someone about that. We have a huge number of properties that are coming online. Our primary kind of claim to fame is thermodynamics. So phase diagrams, being able to understand what's theoretical material that might be possible versus probably not possible. And then all the properties are associated with that. So, the mechanical properties are basically related to kind of how you can nudge the atoms around, or really the cells, the lattices around, and how they respond that way. To mention phonons, we have piezoelectric and dielectric tensors. We have coordination analysis, so we're trying to understand the oxidation of various elements in different structures and how those change. Kristin mentioned that we are looking at characterization very, very heavily. It is one of our next big frontiers. So one of the things that are coming out is basically a large database of X-ray absorption spectra that we've computed. The K-edge spectra are already available. The L23 are coming. We're trying to fix some last-minute quirks with the API so that that's available for everyone. We have diffraction patterns that we've computed. We've added some things in there to basically start adding thermal ellipsoids, so we can actually look at kind of the ADPs from those and how those would change as a function of temperature. We have simulated TEM diffraction patterns that are also coming via an app, so you can choose a material, choose what your beam direction is going to be, what your direction for your planes are, or for your sample, what the plane direction is, and you can get the diffraction pattern that way. You can change the accelerating voltage. We're going to add a little bit of aberration, but probably not too complex of a model there unless someone wants to partner with us for that. So having accessibility from fundamental material science is a huge aspect of this.
Actually, one from Kiang Lu. What method do you use to calculate 3D transition metal L2 or 3 edge?
Yep. So we use the FEF code from John Rare at the University of Washington. This is a muffin tin orbital based code. So it's kind of like something between full ab initio DFT and a slight, I wouldn't say approximation, but it's a little more pseudopotential based. And the idea there is that it's fast, it's extremely fast, and we can get a lot of very good spectra for, a huge amount of the periodic table. we've done some benchmarks on transition metals, and the behavior for the primary peak isn't too bad with, kind of the limited kind of benchmark sets that we were able to find. Cobalt oxide, iron oxide, those kinds of systems. But if you want very precise X-ray absorption spectra, this isn't the data set for you. You need to compute your exact situation. That's another thing, is that this is general, it's perfect materials. There's always going to be deficiencies, but they're good enough for a lot of purposes. So another question, could MapMiner access the different scopes of database provided by MP? In the extremely case, the whole database on a specific parameter, how do you define the scope of the database that you would like to pull the data out of? Is this something that's defined already? So MapMiner has, so the way you get data out of Materials Project is through our API, and MapMiner hooks into that API. So you can get most things from the Materials Project via MapMiner alone. That being said, you do need an API key. So let me just stop sharing and just very quickly share one thing that's important for anyone who wants to get data. So this is what Materials Project looks like once you've logged in. There is this dashboard button at the top right, and then you have an API key. This is what gets you access to Materials Project data in general. So you generate your own API key. This is still free, and you use that API key, you can access most of the things in the Materials Project right now. There are a few pieces of data that we didn't do the best job of making APIs, so they're not exactly the most accessible. And everything moving forward, all the X-ray absorption spectra, all the phonon spectra, everything we're doing new is going to be API based. So anything you can do with the Materials Project website and that's coming new, you can basically do via the API or get that data if that's all you really care about. And you can, in MapMiner, via that API client, you can kind of control what it is you get, whether that is the data set in terms of which materials you're looking at, or the data set in terms of which properties you're focusing on. Any other questions? I lost my chat window, so I don't know where that went.
So could you look at the first question above?
Oh, okay. Oh, I didn't even see that, sorry. Are you expecting people to only need to use Jupyter Notebook interface to perform the analysis or take care of majority? Okay, so this is one of the things we were talking about a little bit earlier. Jupyter Notebook is great for a lot of things, but we understand that Python and Jupyter Notebook might be inaccessible to a huge amount of the community simply because it's Python. You have to learn another language. And once you get into Python, you have to really learn all the tools that are available. It's not sufficient to know the language. The tools are what make this really useful. So scikit-learn, pandas data frames, NumPy, it can be kind of an alphabet soup, just like any kind of domain science, right? So what we're trying to do is make these tools more accessible. And so the machine learning is probably not going to get there anytime soon because it's just very hard to do. You need to kind of scope your problem, be very careful about what you're doing, but all the tools that are associated around it. So I'll show you a very cool app that we have on Materials Project. It's called Crystal Toolkit. So Crystal Toolkit lets you do all the manipulations that we kind of do in Python. It loads up, has right now a random material. So you can kind of look at the structure of that material. The bonds are shown, which elements you can kind of rotate around, look at what's going on. You can download an image. But the really powerful thing is this transformations. So if I click on this, I can basically make this into a slab. So a slab is just a single surface. So I say enable transformation, and this will just take a little bit of, and basically it's made a slab. Now, because this was a really simple unit cell, the slab isn't anything special. I can change the Miller indices for the slab that I want. I can change the slab size. I can also change this so I'm actually adding a supercell. So I will make a slab, then make a supercell. And because this is a very simple supercell, I'm going to modify it. I'm actually going to change that. And it'll set, you'll see it's computing. Oh, that didn't work. Turn this off and then turn it on. Oh, there, it is a simple supercell. So you can kind of see that there's the two there. So it's not the most intelligent right now based on order, but it is something that lets you use the Python tools that are already available. And we are trying to continue to increase the kind of availability of these kinds of tools. So theoretically in the future, you could go ahead and say, I want to build a grain boundary, which that is one of the transformations here. Build that structure and then compute whatever you want on it. You can actually submit it to the materials project here, and that will let you submit it to us. We'll compute it, and then we'll build a materials property detail page for that. Oh, new message. Cool.
All right, so it's 1+3. Is there any question? Now is your last time to to say. But well, thank you very much, Shyam, for this introduction and tutorial. It's really impressive and easy to use. I will try to put the video online ASAP, and then send an email to the people who participated. And I'll try to also gather some useful links for anyone interested. So yeah, give me a few days so that I can compile this. But yeah, this is I'm really excited by what you can do with this. So yeah. Well, thanks again. I'm gonna clap alone because everyone is muted, but but yeah, thank you so much.
Sounds good.
So yeah, well then, bye everyone. Have a great day, and well, thanks for coming. Bye.